Good morning, everybody. Today we are starting on chapter 21. We're going to spend about a day and a half on it. It is all dealing with enols and enolates. So enols and enolates are something we talked about a little briefly a while ago. So there's two different ways. Well, it's making an enol versus making an enolate. If we add in a strong base, with a ketone or an aldehyde, and we can just use NaOH for this. We'll be able to pull off this proton here. This has a resonance structure where we can put the charge in the oxygen. And then from here, that oxygen can pick up the proton that we originally pulled off. And it's going to give us what we refer to as an enol. So this is our base catalyzed mechanism. It's referred to as a tautomerization because we're pulling off a proton and putting it somewhere else. We could also do this in acid. We're going to get an enolate instead of an enol. I guess we can get either. No, they guys can build either. Okay. I'll take a ketone. We can pick up a proton if we're an acid. So H3O plus here. And then that water we made can again pull off a proton, stabilize this here, and form an enol. Okay, so different compounds have different pKa's, which can determine how easy it is or hard it is to deprotonate this. So for instance, our ketone is actually going to be our most difficult thing to deprotonate. As its pKa is around 19. Versus an aldehyde, which is a little bit more acidic. Versus some other compounds we're going to use a lot. A diketone. Actually, no, wait. So at least one. I guess our diester is going to be our next if we're going in order. Going to have pKa of around 13. The ketoester, which is a combination of a ketone and an ester. pKa of around 11. And then our most acidic for these reactions we'll be talking about is just going to be our diketone. pKa of around 9. So what does that mean? It means if we have an aldehyde and a ketone in solution and we add in a base, because we have a pKa of 17 versus 19 here, the likelihood of deprotonating on the ketone versus the aldehyde is going to be the difference to the second, or to the, no, to be 10 to the different power. So our difference here oops, so 19 minus 17 is the same as 2, which is 10 to the 2, which is 100. So there's 100 more likelihood of deprotonating on our aldehyde versus our ketone here. So if I add NaOH in solution with the two of these, I'm going to make this negative charge on my aldehyde because it has a lower pKa. If you want to work with the math, you can, but for the most part, just lower pKa means that's the one that's going to get deprotonated. All right, with that in mind, we're gonna start doing some reactions. The first one is pretty straightforward. If we take any of these compounds and add in acid followed by Br2, so I'm just gonna grab a ketone. We're adding an H3O plus. We're gonna end up adding no, not aromatic. What am I doing? Br to this, what we're going to refer to as the alpha position, or the alpha carbon. So the way this works is we are going to form an enol. So we're going to pick up a proton off of our H3O plus. This water can then deprotonate to give us this enol here. From this point, if we throw in Br2, we will do an attack on this bromine to brominate our alpha position. And then our water can ball for proton. To give us our final product. Oh, so the alpha carbon is just one position away from a carbonyl. So wherever your carbonyl center is, alpha just going to be the next carbons over. So this is an alpha carbon. Same thing with this here. Sometimes they're the same, sometimes they're different. Like these two alpha carbons are different, but on the other side, they would be the same. So sometimes you get symmetry, sometimes you don't. We can do this with a slightly different set of reagents for carboxylic acid. I'm not going to go through the mechanism for this one because it's kind of complicated, but doing a very similar reaction if we take carboxylic acid. The alpha carbon of this is still 1 away from our carbonyl. We're going to use a slightly different set of reagents for this. We're going to use BR2 and PBr3. Followed by water. This is also going to let us brominate here. All right. So the first couple of these have been doing this in acid. If we do it in base, it works. It just tends to work really well. So if we take, for instance, this compound here, throw in NaOH. So now throwing in base and Br2. Pull off an alpha proton. This can attack a bromine. To give us a bromination product. The issue is that once you've done this, this is actually going to be more acidic because that Br is there. Than it was over here. So you're, instead of attacking another molecule and doing this again, it's just going to attack this molecule again. It's going to pull off that proton. All right. Attack another Br. And dibrominate. Right, a reaction up top. So adding in NaOH and Br2. Stop doing that. Is going to result in dibromination because once you pull off the first proton and brominate, you made a more acidic center. So it's going to want to go at that center again. If you were to try to do this in just one equivalent, of base. What you end up making is essentially 50% dibrominated at 50% that's not brominated. Because once you've made this product, this is more acidic, it's just going to react with that one twice, as opposed to just reacting once and then starting over with a new one. So we pretty much always do this in excess. Because of that, sometimes it's written, but usually it's just implied. It's such a good brominating reagent that it'll actually do it 3 times. If we have a terminal bromine, or I guess 4 times. So if we have something like this here, where we have 2 alpha positions, let's make them unique. Adding an NaOH, Br2, it's going to pull up every proton it can and brominate it. So for this here, we'd end up tribrominating. If you have a terminal bromine or terminal ketone, so a methyl group on one side, and you had NaOH and Br2, this is going to tribrominate. And at this point, this is actually a very good leaving group. It's pretty equivalent to an acid chloride. So if you throw in H3O plus, you can do what you would do with a acid chloride here. We're going to end up kicking out. So you'd have water come in. I guess it'll happen in the previous step. Yeah, so before H3O plus actual step, we'd have an NaOH still in solution. We can kick out this CBr3 because it is a good leaving group. Which can give us a carboxylic acid plus CBr3 minus, which can pick up a proton from H3O plus. So if you have a terminal ketone here and you throw in these set of reagents, so NaOH and Br2, this is going to let you actually break off that N carbon and form a carboxylic acid. Kind of an odd reaction, but it does occur, so we should probably go over it. Okay, this is going to bring us to one of the main reactions that we're going to talk about today, which is the aldol addition. So what the aldol addition is that we take an aldehyde or a ketone, throw in base, so NaOH, the reagents for the last problem were NaOH, Br2, and the second step was H3O+. All right, so throwing in just NaOH lets us deprotonate and this can attack another equivalent of itself. We're going to end up forming a carbon-carbon bond. So we have our original molecule. And now we formed a bond to that second one we attacked. From here, we can pick up a proton from that water. Draw some blue. A little more. To give us our aldol addition product. So it's made up of two components. Both of them were originally our starting aldehyde here. So we had, I'll draw one of them in black, the other one in blue. The one that was in black ended up attacking the one in blue. And you can see that those two components are still there. You can count the carbons on them to give us these two products. Let's do another one of these. Let's take a ketone. I'm going to dry up both equivalents of it. Plus NaOH. I'm going to deprotonate one of them. the one I deprotonated can then attack the other equivalent. We'll make one bond to that equivalent plus the 2 methyls and oxygen it has. That oxygen can pick up H plus from water. To give us this aldol product. From here, there is another step we can do if we heat the reaction. I'm actually going to redraw another one just to kind of go through it a third time before we do that. So let's take it just a completely different one. We're going to take another aldehyde. Take this ethyl aldehyde here. This time we're going to do the reaction heat, so NaOH. We're strong over it. And heat. So originally we'll pull off the proton. Generate this negative charge. Pick up your H plus from water. And then from this point, because we're in heat, we're going to be able to do kind of this interesting proton transfer. So we're going to have our OH minus attack here. It'll let us eliminate our OH, which is then going to grab the proton from water. We're going to end up forming a double bond. And give us what's referred to as the aldol condensation product. It's condensation because we eliminated water to form a double bond at the end. So your double bond is always going to form between your ketone and your alcohol. So it would always be this position here. Let's do a couple more of these. Maybe do a cross one and then take a couple minute break, maybe like a 10-minute break. So here it is, the ketone. In our first step here, we pull off proton. Oh yeah. Attack our other ketone here, forming a bond between our alpha position to that other ketone. We'd originally make it an O-, then we could pick up proton. From this point, we can pull off the alpha proton again. Eliminate this water. And we get form our aldol condensation product. All right, so these are the simple versions of these. We're going to do what's called a cross aldol next.
Can you go back for a second, please? Thank you.
So cross aldol is where we have two different aldehydes or ketones. We're going to do one with an aldehyde first. We're not going to do the condensation portion yet. So we're just going to do forming the alcohol. And then after the break, we'll come back and do it as condensations. But if we were to take this solution here, so we have two different aldehydes now throwing NaOH. It can give us a bit of a mess. So the first thing that can happen is we can either pull off this proton or the other one. I'm going to draw this proton pathway first. I'm going to draw it out twice because there's two different possibilities. It can either attack itself or the other aldehyde. If it attacks itself, it's going to make one product. So we're adding to this alcohol with one carbon versus if we attack the other aldehyde is one carbon longer. So we need almost the exact same product. We now have an extra carbon on there. So if I'm looking at these two reactions, this reagent versus this reagent, the only difference is this carbon here. It's only different in our product. Should be this carbon. Okay, other option is to instead attack this proton. We can make two different products from this. So we'll make an aldol or an enolate. It can either attack itself. Well, I'll draw the other one first. The other starter material or itself. So if it attacks the other starter material, our product's going to have that original structure plus a bond from our alpha position to our starter material. So it has an OH and one methyl group here. And then for our final product, should be one carbon longer on the end. To give us this product here. So none of these are all like the major products. There's no one that's going to be more favored than the other one. They're all slightly different. You look at them, this methyl's here versus having two methyls. So none of them are symmetrical in any way or like the same compound. They're all unique. Technically, we could heat all of these up and eliminate all of them, which we'll talk about in a little bit. So this is our cross aldol. It is a messy reaction. We'll talk about a little bit of ways to make it a little less messy. But for right now, this is basically our four product reaction. And it will pretty much always give you four products. There's only one way to make it not, but we'll talk about that in a minute. So we're going to take about a 9-minute break, meet back here at 10:10, where we will do a lot of the rest of 21. We won't finish it today, though. So, but a 9-minute break.
Sorry, I just have quick questions about the product. So that means if reaction like this, we will have 4 products total.
Yep, 4 products.
That's, yeah, all of them are major.
Yep.
Thank you.
You're welcome. All right, so let's do one more of these. We're going to do it in heat. So this time we're going to actually do our condensation. Yeah, start one. So first up, okay. First up, we're going to pull off proton. We're going to draw this out twice. It can either interact with itself, and then because we're in heat, we could pull this off, pull off our proton again. Get our condensation react product. Like so. So that's product one. Product two is where this is going to interact with our other aldehyde. We can eliminate. To give us product two. All right, our other options, we can pull off the other proton. This can either react with one equivalent of the starting material, the first starting material, or itself. Or two equivalents of the other starting material. Nope, skip a step. and this will give you your 4 products. So these products kind of look terrifying, but if you kind of break them down, they're always composed of basically this backbone going to this here. The only difference is that sometimes you'll have extra things off of these 2 positions. So if we take a look at the first one, the only difference between this and this here is that because we had an extra group here, we add one on to this position. Same thing in the next one, we had an extra group, and we had 2 of them, so we added 2 of them. So you always have this exact structure to your product. You just have to start adding in some different groups depending on what you're reacting. Okay, so there's a couple of different things we can do to try to reduce the number of products we have. Yep, it'll always be E, give you an E product. It'll never give you a Z one. So your double bond will always be E. Something we talked about earlier was that if we take, or if we look at our pKa table, our pKa for a ketone is 19, and our pKa for an aldehyde is 17. So because of that, the aldehyde is 100 times more acidic, because it would be 10 to the 2, which is 100. So if we have a solution with both an aldehyde and a ketone in it, I'm going to erase this over here. Now when we add an NaOH, we essentially only get the aldehyde because it's 2 pKa units and it's logarithmic. Our ratio of these 2 enolates is going to be 100 to 1, which is a large enough number that we can essentially just forget about this side here. So now we're only going to get 2 products. This can either interact with itself to give us a product, or it can interact with another equivalent of their ketone. So we get some selectivity when we have both a ketone and an aldehyde in solution. Oh, come on. And this is going to take us down to just 2 products. which is realistically going to be about as good as we're going to get for these. Another thing we can do is we can add in an irreversible base. So NaOH can pull off a proton, but then it could go back on, it could go off, and it could get pulled off on the other side, on the other atom. So to fix that, there's two different bases we use if we want this to be irreversible. The first one is either LDA or NaH. And let's talk about why we would use one versus the other. It's really just large base versus small base. So something like NaH, if we added this in first, it's going to make H2, which is a gas, and it'll just like bubble out of the solution. It'll be gone. It won't be able to be reversed because it's no longer in your solution. So if you did this in two steps, where you first added NaH, and then as a second step, added an aldehyde, you could somewhat control your reaction. And you probably still end up with a mixture of the two products. I'm just going to draw the cross-coupling one. Well, I guess I'm just going to do that. And this somewhat lets you force getting both the ketone and an aldehyde in solution, or a ketone to attack an aldehyde instead of an aldehyde to attack a ketone. So by adding in a base first and then adding in your second reagent, this lets you somewhat also control your reaction. You're still going to end up with your other product, which is where it attacks itself. But this at least lets you have a ketone attack first. Another thing you can do is LDA would be a large base. So if we had a more interesting ketone, where we have two different alpha positions, now if I add in a small base like NaH, I'll selectively deprotonate on that more substituted position. I'm going to flip the molecule over. Could do an attack. Form this product versus if I use a large base like LDA. So LDA is lithium diisopropylamine. We're now going to selectively deprotonate on the other side because you're using a large base. It'll pull off from the less substituted center. And this lets us get a different product where we attack from the other end. So kind of large base and small base rules still apply just like they normally would. large base will pull off your more substitute, or sorry, large base will pull off your less substituted versus your small base will pull off your more substituted, and those two will give you different products. And this is what's called your cross-coupling product. Sometimes you'll see it written as it'll tell you to just draw the cross-coupling product. There are some ways to try to force it in solution where you're like diluting certain things, but we're not going to talk too much about lab techniques. Okay, we're going to move on from the aldol, talk a little bit about the Claisen condensation, which is a little bit more straightforward. The Claisen condensation is going to involve esters. There is still a cross Claisen, which will give us 4 products again, but we can talk through that in a minute. So our normal Claisen condensation is going to be where we take an ester, we're going to throw in base, this is going to attack another equivalent of itself. And this is going to be where the main difference is going to come in. At this point, these electrons can come down, kick out this OET, and give us a product. Which is going to be this keto ester here. So if we're able to actually eliminate ethanol from solution, this allows us to generate this dicarbonyl compound, whereas before we were getting alcohols that were being treated with heat in order to eliminate and give us our condensation products. So this is the final product from this. If we do this with 2 reagents, we can do what's referred to as a cross Claisen, where we end up with 4 different products. So let's go through one of those. So 2 different esters. If we have them in solution, we're always going to use the same base. as whatever ester is. So you have OET here, you're going to use OET minus as your base. It's going to prevent doing an ester switch where you end up, if you use methyl ester here, you might end up with a methyl ester in the end. So we have a bunch of different possibilities for this. Start by first pulling off the alpha proton of this ester on the left. There's two different products that can form. It can either interact with itself, or can interact with our other ester. We can have our second ester to be deprotonated. It again is going to have two different possibilities. Either interact with the other starting material or itself. If it interacts with the other starting material, should get this product. Oh no, I gotta redraw this. There we go. If it interacts with itself, it looks slightly different. It's gonna have an extra isopropyl group down at the end. Oh, it's choppy. Come on. And you get these four major products. I'm gonna give you guys a minute to get caught up on drawing these. Similar to with an aldol, we can try to force one major product through adding in LDA or NAH. Because there's only one side to these, it's an ester, there's not two different sides, you're not gonna really get that selectivity with like the large base, small base concept. But if we were to do this in 2 steps, first we added an LDA. Oh, I have an R here. I get an ethyl. Followed by adding in an ester. This is going to give us a little bit more selectivity to try to force this towards one answer or one product. We didn't really talk about this with the aldol. We might talk about it on Tuesday, but you can do what's called an intramolecular claisen or an intramolecular aldol. So for an intramolecular claisen, we're going to take a large diester. So something with maybe 6 carbons in between the 2 ester groups here. If we add base to this, symmetrical, doesn't matter which side you're pulling off proton from. We can make an enolate. This can then attack itself. We're going to form a ring. So we're going to form a 5-membered ring from this. Because we have 1, 2, 3, 4, 5 carbons in between the attack. Then our last step, we will eliminate this OET from our ketoester. To give us this product. Your ring size is always going to be essentially the difference between your 2 centers minus 1. So if we have 6 carbons here at the start, you guys are pulling off from our alpha position. We're going to have 1 carbon that is not part of our ring. So if you have 6 carbons in your diester here, you're going to end up forming a 5-membered ring. If we do a larger one, 1, 2, 3, 4, 5, 6, 7. When we add in our base, we'll deprotonate. Let's call this carbon 6 here. Six is going to attack 1, giving us a 6-membered ring. Plus this methyl ester still on here. We can kick off this OME and generate our final product. These can get a little complicated if you don't have a perfectly symmetrical ring. So let's keep this ring here. We're going to add a methyl group to this. Let's add it here. So now there are two different possibilities. Actually, let's make it over here. When we pull off this proton, we're going to make one of our two products. We are going to make a ring between carbon 2 and 6, which means this would be a 5-membered ring because 2, 3, 4, 5, 6 would be 5 carbons in between them. I'm going to kind of quick hand this last part. If we have a bond between carbon 2 to generate this here, as I'm counting around my ring, this would be 2, 1, 3, 4, 5, and 6 here. We made the bond to 6, so that's where our ketone ends up. And then we need that methyl group coming off 4. Our other product is where we deprotonate it on the other end. So if we deprotonate position 5, this is going to get messy. I'm just going to redraw it again on the top. Again, because we have that methyl group, it makes it asymmetric. We can make a different enolate. It's going to lead to a slightly different product. I drew this weird. Where we're now attacking the other ester here. If I count my ring the same way, although I'm just going to count left, right? That makes more sense. 1, 2, 3, 4, 5, 6 here. We're making a bond between 2 and 6 again. So our ketone is on 6. And now that methyl group is on 3. So for this intramolecular clays in here, we're going to end up with 2 different products. One of them where this methyl group is on the 3 position, the other one where it's on the 4 position. So these are pretty tough. We'll do a couple of these at the start of class on Tuesday. I think I'm going to stop here for today. This is kind of a good logical stopping point. I will see you guys in recitation today. We're going to go over chapter 20, and then we'll cover 21 on Wednesday in recitation. So have a good Tuesday or Monday. I'll see you guys in an hour or less, depending on when your reci is.